In this video, we're going to consider unitary operators, and we're going to begin with some definitions. So suppose we have two inner product spaces. V and W, and they're over the same field. And that's we're going to be dealing with the field is going to be real numbers that we're going to deal with. And so we have these two inner product spaces. Of course, remember, inner product spaces are vector spaces that have an inner product defined on it. And let T be a linear transformation from V to W. So we have this, that's the background we have here for our definitions. And we have these two definitions. One definition, T, our linear transformation, is said to preserve inner products if we have this. If you take the transformation of V, transformation W in the inner product, that's going to be equal to VW, and that has to be true for all V and W in the vector space V. So if this is true for all vectors in the vector space V, then T is said to preserve inner products. And another definition we have is an isomorphism I guess I should say an isomorphism of V onto W is a vector space isomorphism T of V onto W, which also preserves inner products. Excuse my writing. So again, T is said to preserve inner products if this is true, and then an isomorphism is a this transformation from V to W, which preserves inner products. So this would be, so if this preserves inner products, then it's an isomorphism. A lot of books will just say, well, I'll get to it in a minute. But there, a lot of books have another way of defining this, mainly that it preserves norms. So let me actually just mention that real quickly. A lot of books will say something like this: an operator or transformation in our context is called an isometry, and that's ISOMETRY, if the transformation or operator preserves norms. Once again, for all V in your vector space. Let me put that in parentheses. T preserves norms. So there's a couple of ways you can define an isomorphism or an isometry. You can either think of it as preserving inner products or preserving norms, depending upon your definition. And we'll see here in a minute that these are equivalent. If you have one, then you have the other. In fact, let's go right to a theorem. And before we do this theorem, I'm going to need a relationship, and you may be familiar with it, so I don't want to spend a lot of time on proving it. So let me just show it to you, and then we're going to use it here in a minute. So it's this relationship here that if you have a transformation and you have TU, TV, that's going to be equal to the norm of TU plus TV, the norm squared minus, actually I left off a square over here. There should be a square up there too. Minus TU minus TV squared over 4. So we're going to use this relationship in one of the proofs. So I'll just mention here again, you may have seen it before, so I want to spend too much time on it. And this is true on a real inner product space. When we're dealing with real numbers, you have to have a little bit different if you have a complex inner product space, but it's the same kind of idea. And so let me just go through the proof real quickly. Like I said, I don't want to spend a lot of time on it if you're familiar with it. So again, we're going to start with the left-hand side here. And then we're going to expand it. And of course, the definition of this norm, just like for any time you have a norm, you'll have that, say if you have TV squared, of course, that's going to be equal to TV like this. And so for this first step here, same thing here, we're going to take what's inside the norm, just like we had here, and put it in the inner product on both sides. And so we have this here, put it in the inner product right here. And same thing over here, put which we have here in the inner product. And then, of course, now just use all the rules of the inner product. And you should do these step by step. So, like, for example, we can say that this here, right here, is equal to this plus this. In other words, I'm just keeping this the same. One of the main rules of the inner product. This goes with this, and this goes with this. Same thing over here. This goes with this, and then this also goes with this. I'm just using the basic rules of the inner product. And then I'm going to do the same thing in another step. I'll put this inner product with that, this inner product with that, this inner product with that, this inner product with that. And I'm doing the same thing with this one. Now I'm going to factor out the negatives where appropriate and do the work with the signs. And when you do that, like here, of course, this is going to be this with a negative in front. Now this is going to have a negative sign, but there's going to be a negative distributed here. Same thing over here. This will be like a negative of a negative. That would be positive. And here we'll have two negatives, which is positive, but we'll have a negative in front, so we get this. Now, when you look at this, you'll notice that we have a negative, we have a positive TU, TU, and we have a negative TU, TU. So those are going to cancel. Then over here, we have a positive TV, TV, positive TV, TV. So we're left with these four terms here. We have two TV, TUs and two TU, TVs. Put those together. And of course, because this is a real inner product space, we can flip these. Normally, we would flip these and do the conjugate, so we can. But since we're dealing with just real numbers, we can flip these, and that'll be equal to this. So again, because this is a real inner product space, we have this. So once again, if you want to look at the more detail, you can just slow the video down and take a look at this more detail. But I just wanted to go through that quickly. Again, we'll use that here in a minute. So now we're going to be aiming towards we're calling unitary operators. And I'm going to start using U now. And let me give you this theorem. Again, the transformation, again, I'm just calling it U for a linear transformation. Linear transformation on an inner product space. And call the linear transformation, call it U on an inner product space. The following are equivalent. Again, a lot of books will just say that T, F, A, E, the following are equivalent. Number one, the adjoint of U with U is the identity. Number two, the transformation preserves inner product spaces, inner products. U preserves inner products, again, for all V and W in the vector space. And again, this is preserves inner products. And finally, number 3, the transformation preserves norms. So these 3 things are equivalent. And of course, remember what that means. That means if this one is true, the first one's true, so are 2 and 3. And it also means if 2 is true, 1 and 3 are true. Or if 3 is true, then 1 and 2 are also true. So those are all equivalent. So let's prove these relationships. And I'm going to do, in some of these cases, I'm going to do more proof than we really need, just to give us some techniques on how to do some of these proofs. And so suppose one is true. And of course, we're saying suppose that that's true. The adjoint with U is going to be equal to the identity. So now we want to show 2, assuming that 1 is true. So we'll start with the side here. UV, UW. And of course, we can just use the definition of the adjoint. This. And then, of course, from 1, we have that this is just I. Like that. So that proves that 2 is true. We assumed I was true and just did the adjoint here. Then from 1, we had this. We got that. Then, so now, suppose we've proven 2. So now suppose 2 is true. Now, again, we want to prove that this is true. And we'll just square this. Once again, by the definition of the norm, we have that that's true. And then from 2, since we're assuming that 2 is true, we can use the fact that U preserves inner products. So we can say this is going to be V. And then finally, of course, by definition, if these are the same, we have an inner product, this is going to be equal to V squared. So we've proven that if 1 is true, then so is 2. And then now we've assumed 2 is true and gotten 3. So we've kind of started here. This implies this, and this implies this. So that means you can go from here to here. So once you know 1 is true, you have 2 and 3 to be true from this. Or if you know 2 is true, you have that 3 is true. Now we have to kind of go the other way a little bit to cover all the bases. So let's start with, so now we're going to start at the bottom. So suppose 3 is true. And of course, we're supposing that UV we're assuming we can preserve norms. And so now, let's start with, so again, we want to, what are we looking to prove? We're looking to prove that it preserves inner products, starting with the fact that it preserves norms. So let's start with capital U, V, W. And we're going to use that relationship I showed you a minute ago. We're going to use this relationship right here and say that UV plus UW squared minus UV W squared all over 4. So again, just using that relationship here, we're getting that U, these are all capital U's here. We get this. And then, of course, use a linear transformation so we can sort of factor it out. This. And then now, since we're assuming that 3 is true, we're assuming U preserves inner products. Excuse me. We're assuming that U preserves norms. So we can say that this is equal to this right here. And now we're going to go the other direction using this theorem that we looked at before, that if you have something here, you have, say, TU TV minus TU minus TV, that's divided by 4, that's equal to this. But in our case, we're going to have just V here and W, V and W. And then if we go backwards, this all comes out to be V and W, like that. So again, so we found that 3 is true, so is 2. Now we want to start with 2 and see if we can get 1. So suppose 2 is true. That is that we preserve inner products. So we're assuming we preserve inner products for all V and W in the space. Now let's start with this. Start with U, adjoint U. Minus the identity U, V. So we're starting with this. And now just doing our usual stuff here. We can make this into U, 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 minus the identity times U, which is just going to be U like that, V like this. And then, so now let's break this up. U star U V, and then I'll put this with this. I'm going to bring the negative in front. U V like this. Then again, by the definition of the adjoint, if we move it over here, the adjoint goes away. All I did was here just just did the opposite of what we usually do. Remember, if we bring this over here, we have to make the adjoint, but if we go backwards, bring it here, the adjoint disappears. We have this, but these two right here equal. Notice this is equal to that. So these are just going to cancel. This is going to be 0. And notice that this is true. Again, I just started with arbitrary u and v. So this is true for all u and v. So we just showed that for all u and v inner space v. So now what can we do with this? Since this is true for like any arbitrary v, we can set v equal to this over here. So set that equal. Again, because this is true for all u and v. Then if we put v up here, we end up having uv minus I u. These capital ones are all u, even though my writing is very messy. So we have that this is 0 for all u. And of course, the only way that this can happen by the rules of by the rules of inner products. Sorry for my voice, but in any case, by the rules of like inner products, if this is true for all u, then this has to be 0. Again, this is u adjoint u minus I, u adjoint u minus I. That's 0. And then that means that has to be 0. Another way you can think of this is this also implies that the norm is 0 for all possible u's. And so we have some theorems that say that if you have that this is 0 for all possible vectors u, then this must be 0. And then finally, that implies that u, I keep writing my u's in different ways. Which is what we we're trying to show. We were trying to show that this was true. So in this last part here, we assumed 2 was true, that we preserved inner products, and then we went through and started with this relationship and proved that that had to be 0 for all u and v. And then, so in other words, that had to be 0 for all u and v. Then we just set v equal to this and plugged it in. So these are identical now, and that was 0. And of course, you remember from the definition of the inner product, if these are the same and we get 0, that means that this and this are 0. But if it's true for all u, then that means this factor, u adjoint u minus I, has to be 0, and we get this. So 1 is true. So we covered all the bases. We started with and let me find my original sheet here. We started with this and proved if this is true, that this is true. And if this is true, this is true. And then we started here and proved if this is true, this is true. If this is true, that's true. So these are all equivalent. If one of these is true, so are the other two. And that's a very important relationship. Now, one more thing that sort of came out of this last step here is something really important. Notice, and this deserves an explanation point here. Note that since u equal I, this implies, of course, anytime you would have an operator, transformation, or anything, when you multiply something by u and you get I, that implies that this has to be the inverse of u. So that means this adjoint, and again, these are supposed to be like the star here, is equal to the inverse, like that. That's very important. And from the definition of the inverse, we have also that this is true. So again, this implies that this is true. And then furthermore, we could say that u adjoint u is also equal to the inverse. Now, you could have also gotten that another way. You could have, when you did this proof that we just did, you could have started with u and the adjoint of u here. And I think that would be the way we could try it. It'd be one of these combinations. But I think it'd be u adjoint u minus I and go through the same steps. And then we would end up getting u adjoint u minus I is 0. and then we would have gotten that U adjoint U minus I is 0, which would have meant U adjoint U is equal to I. So you could get this as well from that same way, or from some of the rules of inverses as well, you could get that this is true. But in any case, this is very important that we have here. So, and this will come up a lot in the future. If you have any of these to be true, if you have any of these to be true, the others are true, but also if any of these are true, then that's saying the adjoint of U is equal to its inverse. And very important. And that's one of the main characteristics of a unitary operator. And so again, what we're getting to here, these are the U stands for unitary. And now we have a definition. An isometry on an inner product space is called a unitary operator. And remember, we said an isometry preserves inner products. So again, this is just one definition. You'll see different definitions in different books. But really, when you go back to that theorem that we just did, and that's why we and everyone usually uses U in that theorem, is because any operator that obeys any one of these is going to be a unitary operator. So from the last, any operator So anyone that obeys those is a unitary operator. And furthermore, once again, you could also say that if U star U, or let me say it this way, if U, the adjoint is equal to the inverse, then U is a unitary operator. Because once again, if you have that U adjoint is equal to the inverse, then that's going to give you that the adjoint times U is I, so you'll have that, and then you'll have all the others. So really, any one of these three implies all the others, therefore it's a unitary operator. Or if you have the adjoint of U is equal to the inverse, it's a unitary operator. Oh, in fact, a lot of books will often give this, especially the introductory books, they'll define this as a unitary operator. And again, if you have this, you'll have these other three as well. Is that unitary operators preserve distances. Remember, like a distance between 2 points or 2 vectors is often defined as, let's say you have 2 vectors, and maybe let's write it as x and y this time. Say where x and y are in your vector space V. The distance between those two is usually defined this way. And then since if U is unitary, then we have U x as U y. And of course, we can factor this out. So we have U x minus y. And since U is unitary, it preserves norms. So we can say that this is equal to this. So we can say that U x U y is equal to U x minus y. So the difference between x and y is going to be the same as the difference between the operator U applied to x minus the operator U applied to y. Again, this is true for unitary operators. So that's another property of unitary operators, is that they preserve distances. And you can also say the product of any finite number of unitary operators. I'm jumping ahead a little bit to matrices here. Is unitary. And you could prove this, sort of formally. You can sort of show it fairly easily, just by, you can convince yourself just by doing a few. Like, for example, let's say if you have, suppose U1, U2, U3 are unitary. Then, of course, what you have is, say, if you do U1, U2, U3, times some on some vector v, then you could think of this as being u2, u3, v. And since u is unitary, it preserves norms. So you could say that this u1 preserves norms, so it's going to give you u2, u3, v. And then, since u2 preserves norms, you could say that this is going to be u3v. Then finally, since u3 preserves norms, you can say that. So you have that this is equal to this for all v in your vector space. So u1, u2, u3 is unitary. Because once again, if we prove that it preserves norms, all those other properties are preserved. And another, I don't know if you really even call this a theorem. There isn't much to the theorem. But if U is unitary, so is U inverse, which is, of course, is going to be the adjoint. And once again, you could do, again, just a short proof, you could say something like this. Maybe if you have V, start with V, then you would have, you can make that IV. You can always put the identity in. And of course, if we put the inverse, replace I with U must win like this. I'm just replacing I with U times the inverse. And of course here, or we could have also put the adjoint, because for a unitary operator, that is equal to the adjoint. And then of course, you could think of this that's kind of messy. Let me fix that. You could think of this to be true. All I'm doing is just applying U to this. So because U is unitary, this is going to be equal to this because U preserves norms. So what do we have? We have V is equal to this, or that. So we started with V, put the identity, replace that with U inverse. Then we're kind of applying U to this vector here. And since U preserves norm, we get this. So we have V equal U inverse V, or, as I said, in the case of the unitary operator, we can say this. So the inverse of a unitary operator, and again, for unitary, that's the adjoint, is unitary. That's something that could be important later. Now we're going to turn to matrices in the same context. And just a couple things on matrices. And we'll consider the complex case, a complex matrix. And again, should say square matrix. And call it the matrix A is unitary if A star A equal I. So now in this case, when we're dealing with matrices, of course, the A star means the conjugate transpose. And just like we talked about before, means the transpose of the matrix and taking the conjugate. Another definition, a real or complex matrix A is said to be orthogonal if A transpose A is equal to I. A real orthogonal matrix is unitary and the unitary matrix is orthogonal if and only if each of its entries is real. And remember from your introductory linear algebra course, an orthogonal matrix A has columns And it'd be the same true if for the rows. That form an orthonormal set. And I'll get an example from, I'm getting an example here from an introductory linear algebra textbook. So consider this. And let's consider the columns. You can consider, like, say, this column here would, say, maybe form, say, this vector here. And this column here would form this vector here. So let's say this, this would be like, say, one element, this would be another element. If you took the dot product of these two, you get 1 square root of 2, 1 square root of 2, minus, I'm going to put this minus in front here, 1 square root of 2, 1 square root of 2, that's 0. And notice each column, the length is 1. So if we take this column here, take the square root of the sum of the squares, this one is 1. But this is going to be a half plus a half. It's going to be square root of 1, which is 1. Same thing, or a half plus a half, going to give a square root of 1, which is 1. So the columns form an orthonormal set. And you remember the same thing, if you had 3 columns, you'd have to be sure all the pairs, when you made the dot product, they all came out to be 0. And that all the columns, the length of them all, if you take a square root of some of the squares, they would all come out to be 1. That's the definition of orthogonal matrix. When you think about it, it would make more sense than a few people call it this way, but the majority don't. It would make more sense to call this an orthonormal matrix because the rows and columns are orthonormal, not only orthogonal. Remember, orthogonal just implies that the dot product is 0. Orthonormal implies that the length of each column is equal to 1. But they call matrices such that the columns form orthonormal sets. They call those matrices orthogonal. Again, it's not real logical. Again, a few places have taken up the orthonormal name, which makes more sense, but most have not. But in any case, that's just a reminder that when we talk about an orthogonal matrix, if you have a real orthogonal matrix, it'll end up being unitary. And a unitary matrix is orthogonal if and only if each of its entries is real. Again, this is the definition up here of a unitary matrix. And there's just a couple more things here to cover. And recall a couple of things. Recall that two matrices A and B are similar if there exists an invertible matrix P such that B equal P inverse AP, like that. You recall that we say these two matrices are similar if this is true. And remember, similar matrices have the same eigenvalues, etc., etc. Now, of course, this can be written in many different ways. Since P inverse is the inverse of P inverse is the inverse of P, and then therefore P inverse is the inverse of P inverse. So you could also say it this way, depending upon how you define P and its inverse, you could write it that way. Or again, you could have these on the other side. You could say A equal P inverse B, P, etc. You don't necessarily have to prove it this way, but just so long as there is a matrix P which obeys any one of these, you'll say that these are similar. So we have something specific for unitary operators and orthogonal matrices. Let me put a definition down for this. B is said to be orthogonally equivalent to A if there exists an n by n, basically a square, orthogonal matrix P such that B P inverse P, like that. So again, P is orthogonal. So if P is orthogonal, and we have this relationship, if P is orthogonal and B is similar to A with this relationship, then we say that B is orthogonally equivalent to A.